Hi everyone. Welcome to ILTA Physics Online. Today we're going to dive into torque, which is the physical quantity that causes rotational motion. From a dynamics perspective, in translational motion, an external force applied to an object creates a change in velocity or acceleration, which moves the object. Rotational motion works in a similar way. An external force acts on a specific spot on an object to create a change in angular velocity or angular acceleration, causing the object to rotate around an axis. This external force applied at a certain point, which causes rotation, is what we call torque. Notice that when I just defined torque, I mentioned both the force itself and where that force is applied. This is a crucial concept. For torque, it's not just about the magnitude and direction of the force. The location where the force is applied is also a vital physical factor. Physically speaking, we can define torque as a measure of how effective a force is at causing an object to rotate. To understand this, let's start with a simple question. What actually causes rotational motion? The answer is our topic for today: torque. Throughout this lesson, I'll explain the three physical factors that affect torque. Finally, we'll wrap up by learning how to calculate the net torque when multiple torques are acting on a single object. But first, let's do a quick review of what we learned last time about rotational motion and circular motion along a path. Up until now, we've been studying non-uniform circular motion where the rotation speed changes. In rotational motion, it's useful to express how fast something rotates as angular velocity, and we define the change in that angular velocity as angular acceleration. As you can see in the formula above, angular acceleration is calculated by dividing the change in angular velocity by the time interval. Depending on its relationship with the direction of angular velocity, this angular acceleration can either speed up or slow down the rotating object. If the angular velocity and angular acceleration have the same direction, meaning they have the same sign, the rotation speeds up. Conversely, if their signs are different, in other words, if they point in opposite directions, the rotation slows down. This is exactly the same as the relationship between velocity and acceleration in linear motion. And then, we also looked at a table comparing the kinematic variables and formulas used in both linear and circular motion. Specifically, linear position, velocity, and acceleration correspond one-to-one with angular position, angular velocity, and angular acceleration. We also saw that the equations of motion we derived for linear movement hold true for circular motion as well. I didn't include the table here for brevity, but please make sure you understand and memorize those relationships. Finally, we summarize the three directions used to analyze circular motion: the centripetal direction, the angular direction, and the tangential direction. The centripetal direction points toward the center of the circle, while the angular direction follows the circular path itself. The tangential direction is the actual direction of the object's instantaneous motion, and it's always perpendicular to the radius. If you have a solid grasp of these three directions, you'll be able to analyze even the most complex circular motion problems. Now, let's move on to today's main topic: understanding torque and analyzing it from a dynamical perspective. Let's shift our focus to the rotation itself. What actually makes an object rotate? As you might guess, this is a question of dynamics because we are looking for the source or the cause of the motion. We can find some clues in linear motion. In linear motion, as we know from Newton's second law, an external force creates acceleration, which causes a change in velocity. In this case, the relationship between the applied force and acceleration is governed by the object's mass. It's similar in rotational motion. An external force applied to an object creates angular acceleration, which leads to a change in angular velocity, causing the object to rotate. But are linear and rotational motion exactly the same? Let's look at the diagram of a wrench turning a nut counterclockwise. To analyze this dynamically, let's define several physical components. First is the pivot, which is the center of rotation or the axis of rotation. Then there's the point where the force is applied. In the diagram below, this refers to point A or point B. And the imaginary line connecting this point to the pivot is called the radial line. Now, I've marked 4 different scenarios of force acting on the wrench with red arrows. Since the arrows in the diagram are all the same length, let's assume the magnitude of the force applied is the same in all 4 cases. The first case is applying force at point A, the middle of the wrench. Here, the wrench will rotate counterclockwise. What happens if we apply the same amount of force at point B, the very end of the wrench? Of course, it will still rotate counterclockwise. But from experience, we know that pushing at point B makes it much easier to turn the nut than pushing at point A. This simple fact is incredibly important. The effectiveness of a force in causing rotation depends on where it is applied. Even with the same magnitude of force, the rotational effect changes based on the application point. Is the location the only thing that matters? Let's look at a third case. We're pushing at point B again, but this time the force is parallel to the radial line. Common sense tells us that if we push directly toward the nut, the wrench won't budge. This means there is zero rotational motion. In the fourth case, if we push at an angle at point B, the wrench will turn, but it won't be as effective as pushing straight up like in the second case. So we can see that the direction of the force is also a key factor. Let's summarize. Torque is determined by these 3 things: the magnitude of the force, the location of the force, and the angle at which you apply the force relative to the radial line. The physical quantity that accounts for all these factors is torque. It's the rotational analog to force in linear motion. But remember, torque is not the same thing as force. The same force can create a huge rotation or no rotation at all, depending on where it's applied. All right, let's get into the math for torque. Torque is the effectiveness of a force at causing an object to rotate about a pivot. One thing is certain. Any force applied parallel to the radial line contributes 0 to the rotation. From our everyday experience, we can see that torque is proportional to 2 main factors. First, the further away the force is applied from the pivot, the greater the rotational effect. Second, torque only depends on the component of the force that is perpendicular to the radial line. Remember, any force parallel to the radial line has absolutely no effect on the object's rotation. If a force is applied at an angle, we can break it down into components that are parallel and perpendicular to the radial line. We only care about the perpendicular component to the radial line. Using simple trigonometry, the perpendicular term can be calculated as F sine phi. As you can see, phi is the angle between the radial line and the force itself. Based on this, torque is the product of the distance from the pivot and the magnitude of the perpendicular force. According to this definition, the unit is Newton meters Nm. There's actually another way to calculate torque. I want you to understand the physical reasoning behind this second method. Let's define the line of action as the extended line along which the force acts. If you draw a line from the pivot that hits the line of action at a right angle, that distance is called the moment arm or lever arm. In the triangle shown, the moment arm times the total force equals the torque. Earlier, we said that torque is calculated by multiplying the distance to the pivot by the perpendicular component of the force. Now, for this second method, we can also calculate torque as the product of the moment arm, which is the perpendicular distance to the force's direction, and the applied force. In conclusion, torque is the product of the distance, the force, and the sine of the angle between them. You might wonder, why learn two ways? Well, in many AP physics problems, especially those involving complex shapes or beams, it's often much easier to visualize the perpendicular distance to the line of action than it is to decompose the force vector. Now let's quickly recap the properties of torque. Torque is the rotational counterpart to force. Though it's technically closely related to the concept of work, which we'll cover later. Also, understand that torque is associated with a specific point where force is applied. As the formula suggests, any force acting directly on a pivot, hinge, or rotational axle provides zero torque, because the distance is zero. We use this concept again when we calculate the center of gravity. Finally, torque is a vector. Just like other rotational parameters, we define counterclockwise as the positive direction, and clockwise as negative. Lastly, let's look at net torque. If multiple forces act on different points of an object, each force creates its own torque calculated by the product of its distance from the pivot and its perpendicular component. In this case, the total net torque acting on that object is determined by the vector sum of all those individual torques. When you calculate the net torque, you must be very careful about the direction. Determine whether each torque is turning the object clockwise or counterclockwise around the pivot, and assign the correct plus or minus sign. If the net torque of an object is zero, the object will not rotate, and we call this state rotational equilibrium. Let's look at a practical example using a fishing reel. Imagine you're trying to reel in a fish. In this setup, we have several forces acting on the reel at the same time, and we need to find the net torque to see if the reel will actually turn. First, let's identify the forces. You are applying a force to the two handles of the reel. These forces are applied at a certain distance from the center, creating a clockwise torque. As we discuss, we'll label this as negative. At the same time, the fish is pulling the line in the opposite direction. This force acts at the radius of the spool, creating a counterclockwise torque. Since it's clockwise, we must treat this as a negative torque. Now, we also see a force acting on the axle, the pivot itself. But remember our rule. Because this force acts exactly at the center, its distance from the pivot is zero. Therefore, it contributes zero torque to the system. To find the net torque, we simply add them up. The negative torques from the handles plus the positive torque from the fish. Now, let's see the result of our fishing trip. Did you catch the fish? If the sum is negative, the reel turns toward you, and you're winning the fight. If the net torque is zero, the reel stays perfectly still. This state, where the torques are balanced, is called rotational equilibrium. That wraps up our introduction to torque. Today, we learned that rotation isn't just about how much force you apply, but where and at what angle you apply it. We also learned how to sum up multiple torques to find the net torque. If the net torque is zero, remember, you're in rotational equilibrium. In our next lesson, we'll take this a step further and look at moment of inertia, which is basically the rotational version of mass. Great job today, and I'll see you in the next lecture.